Hi, in this lesson we will be creating vertex buffers in memory. After that we will ask Vulkan to render those vertices. We will start by creating a new header file called buffer handle. We add the typical pragma ones and then include Vulkan. We also write up the namespace for our course. In this file we will introduce what we will call a buffer handle. When we create some memory for data and give it to Vulkan, we'll get back a vk buffer object and also a vk device memory object. We will use the vk buffer for requesting a render of that data. This is going to be a simple struct. We can now go to the graphics header, and after I include the buffer handle header, I will add a public function called createVertexBuffer. It will return a buffer handle. We will also need to later clear the allocated memory, so we also have to have a destroy vertex buffer. I add both of these signatures in the buffer region, and I create their bodies. Now, when creating a vertex buffer, we will also want to accept a list of vertices. These vertices will be moved to the memory, and I've added this to the header signature, and I also added it in the CPP file. So here I create a new buffer handle struct. And then we need a buffer create info object. We can set the S type. Then the size will have to be the byte size of the buffer. This size is the size of a vertex times the count of vertices. We then have to specify the usage of this buffer. We want to use it for a vertex buffer, so I set vertex buffer bit. And the sharing mode will be exclusive. Now, in this lesson, we're not going to have the buffer on the GPU actually. But in the next videos, we're going to have it uploaded to the GPU. To upload it to the GPU, similar to rendering with the GPU, we'll have to issue commands in the command buffer, and then pass those commands to a device queue family. And some devices might have separate queues specific for uploading data. These separate queues can be used to upload data that is shared between different queues, but each graphics queue also supports uploading data. So our data is exclusive to the graphics queue. Next, we can call the createBuffer function. We have to pass in the device, the buffer info address, no allocator, and finally the address to the buffer field from the handle object. In case this doesn't work, we throw an exception. When destroy vertex buffer is called, we can then destroy this buffer from the handle. Next, we need to actually give the data to the device. To do this, we have certain memory requirements. We can get these by calling the getBufferMemory requirement. By the way, we also need to return the handle. We can then also get memory properties for the chosen physical device. We can do this by initializing a new vk physical device memory properties struct, and then calling vk get physical device memory properties function, passing in the physical device and the new struct address. From the properties, we're interested in the memory types. I will create a span from the memory types count and memory types contained within the properties struct. Then we need to go through the memory types. So I create a normal for loop that increments an index to the memory types count. The first thing that we need to check is if the memory requirements tell us if this memory type is viable. This is done by bit checking the relevant flag, offsetted by the current memory type index. Then we can also check if the memory type's property flags match some conditions. We want the memory to be visible by the host and also host coherent. In this case, the host is the CPU, so host memory is CPU accessible memory. We will also explore GPU-only memory in a later video. So now that we have determined that memory type is one that passes the memory requirement and is also a type that is host accessible and host coherent, we can do an if check and we can set the index of the chosen memory type. And since we will need this functionality later to find memory types that are relevant for the GPU, we can create this find memory type function that returns an index. It will accept the bit mask for the required types and the property flags that we require. I can then cut all of this code here and I will replace the relevant location with the values from the function parameters. We will set the type bits filter here and we also will change the required properties here. We also now have to return the chosen memory type. In case none was found, I will throw a runtime error. Now, to use the physical device up here, we will need to make this function be a class method, which I will do in a moment. We'll first get back down and search for the correct memory type based on the requirement, and also our condition for the memory to be host accessible. Then I go up and copy this signature, go into the header file, and find a place to paste this signature that I copied. Now that we have chosen a memory type, we need to allocate the memory. We can do this by creating a memory allocation info struct. I set the S type, and the allocation size should be taken from the memory requirements. The memory type index is the memory type that we chose. And finally, we can call the vk_allocate_memory function. We pass in the device, the address to the info, no allocator, and finally the device memory handle from the buffer handle object that we created. We can validate the allocation result here for a success. And if it wasn't, we'll just throw a runtime error. Now that we have the buffer handle and device memory, we need to connect both of these up. They are separate since you can allocate memory for a few buffers and bind those few buffers to the same memory. So we call vk bind buffer memory, passing in the device, the buffer, and the memory, and an offset of 0 for where does the buffer start in this memory. When we destroy the buffer here, we can also call the vk free memory for the device memory. The last step that we have to do is to copy our vertex array into that memory. We create a void pointer called data. We also ask Vulkan to give us the memory address of the buffer. We do this by calling vk map memory, passing in the logical device, the memory handle, 0 offset, the size of the buffer, and no additional flags, and finally the address of the variable where Vulkan will give us the pointer to the memory. And sorry, this one is not a function. Now that we have the address, we can memcopy into the data pointer from the vertices data using the byte size. After the memory is copied, we should unmap the memory, calling vk unmap memory, passing in the logical device in the handle memory. This is all we need to create our buffer. Now I will go into the header file. Here we will create a new render function. It will accept the buffer handle, and we will remove the render triangle as we will no longer use hard-coded triangle values. I will quickly implement this in the CPP file. Here at the bottom I create the body of this new function. And the first thing we do when rendering from a buffer is to add a command to bind the buffer to the graphics pipeline. We pass in the command buffer 0 because we are binding the first buffer from an array, Our array is only one vertex buffer, and we pass the address to that buffer taken from the handle. And finally, we need to pass an offset address variable. We're not interested into it, but I have to create the variable above. Now that we have this, we can have the same draw command as with the triangle, but we need to draw a certain amount of vertices. I didn't want to put that number in the buffer handle, since in later videos you will see that we will use the buffer handle for other things except vertices. So I add in one more function parameter for the count of vertices, and I pass in that to the draw call. Also have to correct this in the header. Now, since we deleted the rendered triangle from the header, let's also locate the implementation in the CPP file and delete it too. I will close up the regions now. And when we go to the main, we can now start by creating our buffer handle. We can create the graphics buffer using the function that we added. But to invoke it, we need to pass in our vertices. So I will now construct an array of 3 vertices that have the vertex struct initialized in place. I will pretty much pass the same values that I did in the hard-to-coded shader values. You could instead read vertices from a file if you prefer. So now that this is done, you can pass in the vertices to the create vertex buffer function. This returns our buffer handle struct, and this buffer handle needs to be properly disposed at the end of main. And we can also finally replace this render triangle with a call to render buffer, passing in the vertex buffer handle and the vertices count. I also specify which constructors I am invoking here for more clarity. We're having 3 vertex objects with values for position and color. Running the application again yields the same result with the triangle, but instead this time we're rendering this triangle using memory buffers. When I close the application, I do get a small error message. This message is caused by us not waiting for the device to be idle before destroying our buffers. I quickly build and run to see that it stopped giving this message, and we're in the clear. Now that we have this, we can modify our vertices here in the main file directly. And you will see how we get a wide side of our triangle. We can also try to pass in more vertices now, using this memory approach.